In 1979, a spacecraft captured something impossible, a photograph, just one image, but it shattered everything scientists thought they knew about dead worlds. What they saw was a moon, erupting, not a little, not quietly. This thing was launching material 300 kilometers into space, higher than the space station, higher than anything should go on a world that small, and it wasn't stopping. Fast forward 45 years, we just went back, got closer than ever before, and what we found is so extreme, so violent, so utterly alien, that if you stood on its surface for just 30 seconds, you'd witness geological forces that take millennia to happen on Earth. This is Io, 400 volcanoes, all active, all erupting, right now, in the coldest, darkest corner of the solar system. This moon is burning alive, and the reason why, it's going to change how you think about every moon we've ever discovered. When Voyager 1 flew past Jupiter in 1979, navigation engineer Linda Morabito was doing routine work, checking images, calibrating star positions, standard procedure. But then she saw it. A ghostly umbrella-shaped plume rising from the edge of Io's disk. At first, she thought it was another moon hiding behind it. Maybe a processing error. But when she enhanced the image, the truth became clear. It was an eruption, a volcanic eruption. On a moon that, according to every model, every theory, every textbook, should have been frozen solid for billions of years. The room went silent when she showed her colleagues. Because this wasn't just unexpected, it was revolutionary. You see, scientists had assumed that small moons were geologically dead. Earth has volcanoes because it's massive, with a molten core left over from its formation. Mars had volcanoes once, but they went extinct when the planet cooled. But a moon the size of Io, that far from the sun? It should be an ice ball, a rock, a tomb. But Io was screaming at them. That single plume, later named Pele, was shooting sulfur dioxide 300 kilometers into space. To put that in perspective, if you launched from sea level on Earth and went 300 kilometers straight up, you'd be deep into space, above the atmosphere, above the weather, above everything. And Pele wasn't alone. When scientists looked closer at the Voyager images, they found more and more. Over the next few days, they counted 8 active eruptions happening simultaneously. The textbooks were wrong. The models were wrong. Everything was wrong. That discovery changed planetary science forever. It proved that moons weren't just passive rocks orbiting planets. They could be dynamic, violent, alive. But it also raised a terrifying question. If Io is this active now, what's powering it? Fast forward to December 2023. NASA's Juno spacecraft, which had been orbiting Jupiter for years, studying the gas giant, did something extraordinary. It changed course, swooped down, and flew closer to Io than any spacecraft had in over 2 decades, just 1,500 kilometers above the surface. That's closer than some satellites orbit Earth. And what it captured wasn't just beautiful, it was apocalyptic. Mountains that shouldn't exist, lava lakes wider than countries, geysers erupting in slow motion against the black void of space, and something called Steeple Mountain, a jagged cathedral-like peak jutting out of the chaos like a monument to geological violence. The images are sharp, detailed, almost intimate. You can see the texture of the lava flows, the fractures in the crust, the way shadows fall across ancient calderas. For the first time, we're not just observing Io from a distance. We're there, standing on the edge of hell itself. Let's talk about what this place actually looks like. Io is roughly the size of our moon, about 3,600 kilometers in diameter. If you put it next to Earth, it would look familiar in size, But that's where any resemblance ends. The surface of Io is a nightmare palette. Yellows, oranges, reds, blacks, whites, not from rocks or minerals like you'd find on Earth or Mars. These colors come from sulfur and sulfur dioxide, byproducts of constant volcanic eruptions. It's like someone took a planet and painted it with the periodic table. And here's the thing. There are no impact craters. None. On our moon, you can see billions of years of asteroid impacts scarred into the surface. Mars has them. Mercury has them. Every rocky body in the solar system has them, except Io. Because volcanic activity resurfaces this moon so fast that craters don't have time to form, every asteroid impact gets buried under fresh lava within a few thousand years. Io is erasing its own history in real time. Then there are the lava lakes, Loki Patera, the largest volcanic depression in the solar system. It's over 200 kilometers across. That's wider than the entire state of Connecticut. And it's not dormant. It's churning, glowing, releasing more heat than every volcano on Earth. Combined, imagine standing at the edge of that, not a crater, not a caldera, a sea of molten rock stretching to the horizon. The heat would kill you long before you got close. But if you could somehow survive, you'd watch waves of lava rolling across the surface like a slow-motion ocean. Crust forming, cracking, sinking, melting, reforming. It's mesmerizing, and it never stops. Above these lakes, plumes erupt without warning. Some reach 500 kilometers high. That's higher than the International Space Station, higher than Hubble, higher than anything should be able to rise on a moon with barely any atmosphere. But these aren't water geysers, they're sulfur dioxide. Superheated gas shooting into space, freezing instantly, falling back down as snow. Yes, snow. On a volcanic hellscape. And then there are the mountains. Io has peaks taller than Mount Everest. But here's the twist. They're not volcanic mountains. They're tectonic, massive blocks of Io's crust, pushed upward by the same forces that power the volcanoes. Some of them rise 18 kilometers high, fractured, tilted, standing at impossible angles. Steeple Mountain is one of the most striking. A sharp, angular peak that looks like it was carved by a giant hand. It doesn't belong. Nothing about Io belongs. But it's all there, real, happening right now. So what's driving this madness? The answer isn't inside Io, it's above it. Io orbits Jupiter at a distance of just 421,000 kilometers. For comparison, our moon orbits Earth at about 384,000 kilometers. So Io is slightly farther from Jupiter than our moon is from us. But Jupiter isn't Earth. Jupiter is a monster, a gas giant 11 times wider than Earth. Its gravity is so strong that it pulls on everything around it. Moons, asteroids, comets, even light bends near it. And Io? Io is caught in that grip. But it's not alone. Europa, Ganymede, and Callisto, Jupiter's other major moons, orbit nearby, and they're massive. Ganymede is bigger than Mercury. Europa has a global ocean beneath its ice. These aren't small rocks, they're worlds, and they all pull on each other. This creates something called orbital resonance. Io completes 4 orbits around Jupiter. For every 2 that Europa completes and every one that Ganymede completes, 4 to 1, a perfect rhythm, a gravitational metronome. But this rhythm has a consequence. It prevents Io from settling into a nice circular orbit. Instead, Io's orbit is elliptical, stretched, which means that sometimes Io is closer to Jupiter and sometimes it's farther away. When it's closer, Jupiter's gravity squeezes it. When it's farther, Io relaxes, then closer again. Squeeze, release, release, over and over, every 42 hours, for billions of years. This is called tidal heating. And it's absolutely brutal. Imagine taking a rubber ball and squeezing it in your hand, then releasing it, then squeezing again, over and over. Eventually that ball would heat up from the friction. Now, imagine doing that to an entire moon. Io's interior flexes by 100 meters, up and down, every single orbit. The friction from this constant deformation generates enough heat to melt rock deep inside the moon. Temperatures reach over 1,200 degrees Celsius in the mantle. Magma forms, rises, searches for weak points in the crust. And when it finds them, it erupts. The volcanoes aren't random, they're pressure valves. Io is venting the energy that Jupiter and its sibling moons are pumping into it. Without them, the internal pressure would build until the entire moon fractured. But here's the terrifying part. This process is accelerating. Every eruption throws material into space. Io is losing mass. The more it loses, the lighter it becomes. The lighter it becomes, the more vulnerable it is to gravitational forces. It's a feedback loop with no exit. One day, millions of years from now, Io won't just be volcanic. It will be consumed entirely, torn apart by the same forces that give it life. When Juno made its close approach in December 2023, it wasn't just taking pictures. It was gathering data that scientists had been waiting decades to collect. Infrared mapping revealed something stunning. Some of Io's lava lakes are interconnected. Beneath the surface, magma channels run like veins, linking one caldera to another. Pressure builds in one location, and it shifts to another through underground pathways. It's a planet-wide volcanic network. Juno also confirmed something scientists had suspected. Io's volcanoes aren't evenly distributed. They cluster near the equator and the poles. The reason? Tidal forces are strongest in those regions. The crust is thinner, weaker, more prone to fracture. But perhaps the most haunting discovery was the rhythm. The plumes don't erupt constantly. They pulse. Some last for days, then vanish without warning. Others have been active for decades. Paley, the same plume Linda Morabito discovered in 1979, is still erupting 45 years later. A fire that never sleeps. And Juno's instruments detected temperatures exceeding 1,600 degrees Celsius in some lava flows. That's hotter than most eruptions on Earth. Hot enough to melt steel, hot enough to glow white. This isn't just a volcanic moon, it's a forge, a factory where geology operates on fast forward. Io isn't just a curiosity, it's a key. Because tidal heating doesn't only happen here, it's happening on Europa, where a subsurface ocean might harbor life. It's happening on Enceladus, one of Saturn's moons, where geysers shoot water into space from a hidden sea. Understanding Io helps us understand them. It shows us that moons don't need to be close to a star to have energy. They don't need sunlight to stay warm. All they need is gravity. And gravity is everywhere. Beyond our solar system, we've discovered thousands of exoplanets. Many orbit their stars far closer than Mercury orbits the Sun. They're locked in tidal relationships far more extreme than Io's. Some might be oceans of lava. Others might have crusts that crack and reform every few hours. Io is our laboratory, a place where we can watch these forces in real time. A place where the rules of planetary science are written in fire. And the data Juno is sending back, it's feeding models that will help us understand distant worlds we'll never visit. Worlds that might host life. Worlds that might become our future. Because if there's one lesson Io teaches us, it's this. The universe doesn't need our permission to be extraordinary. Deep in the frozen outer reaches of our solar system, a small moon burns. not from the sun, not from its own core, but from the relentless grip of gravity itself. Io is a reminder that the universe is not static, that worlds don't just sit there. They flex, they break, they bleed, and sometimes, in that violence, they become something extraordinary, the most volcanic body in our solar system. A moon that shouldn't exist, but does, and it's not done yet.